Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell below. We're doing Linear Algebra 1. Chapter 1 is Systems of Linear Equations. We're doing 1.8. This is the last section in this chapter. And we're going to do specifically homogeneous linear systems. These come up a lot in sciences. And they're a specific case because if you have a homogeneous solution, they always are consistent. Why is that going to be? Watch the next scenes. What are we going to do this lecture? Discussion of non-trivial solutions to homogeneous equations. We always know that there's a solution because zero always satisfies homogeneous equations. If there's at least one solution that's consistent, that's the only solution. We call it the trivial solution. Otherwise, we want non-trivial solutions to homogeneous systems of equations. Let's do that. A linear n by n system is called homogeneous if the bi's are all zero, if the right-hand side of each equation is zero. Therefore, we get the general form. It's going to look like exactly like any other linear system, except we mean that the right-hand side is zero in all cases. This is the type of system which is always consistent. Why is that? If you can't come to this conclusion yourself, if I put 0 plus 0 plus 0, I'm going to get 0. Check in the first equation. 0 plus 0 plus 0, any number times 0 is 0. So the zero solution, or what we call the trivial solution, is always a solution to a homogeneous linear system because it solves every single equation, and that's what a solution is. It satisfies all the equations simultaneously. Zero always does that, but zero is not interesting if we're looking for real-world problems for balancing an equation of chemistry or something like this, saying 0, 0, 0, 0 does it using no carbons and no more. Yeah, well, that does balance it, but then you're not doing a chemical reaction, so that trivial solution is relatively uninteresting. What we're seeking is non-trivial solutions to homogeneous linear systems. They're always consistent. They always have the zero solution. We want to know if and when they have non-trivial solutions, and this will come up and creep up and give you nightmares when we talk about linear independence of vectors in M space. So remember that when we're doing linear independence, we're solving homogeneous systems of equations. All right, we're going to solve some linear homogeneous systems now. It's the exact same technique. We're using Gaussian elimination to REF, but this column's never going to change. A lot of instructors will say you can just ignore this, but I recommend leaving it in there. The zeros never change. It's not hard to copy down 0, 0, 0, and then you remember where you're going with this at the end when you get down to the end of the avatar in REF. I immediately augment the matrix. It gives me 1, 2, negative 1, 0, 0, 0. So a lot of people say, oh, you can leave that out because it's never going to change, but just leave it, and it reminds you that it's an augmented matrix from a linear homogeneous system. 3, 1, 2, negative 1, 3, negative 1. I have a leading 1. I want to get zeros below it to eliminate this, so we're immediately going to go row 2 goes to row 2 minus 3 row 1, and row 3 is going to go to row 3 plus row 1 to get rid of those. That will immediately give me 1, 2, minus 1, 0, 0, 0. So copy down, it doesn't hurt. Now what are we going to do? We're going to multiply by negative 3. 3 minus 3 is 0. That's why we did it. 1 minus 6 is negative 5. 2 plus 3 is 5. 0 minus 0 is 0. Those are never going to change. Now what I'm going to do is multiply by positive 1 and just add these together. 0, 5, like that. And then what do we get? We're adding those negative 2. Now, yes, we can do several things, but the mantra is get a leading 1. You ignore Gauss once in a while. He was kind of a jerk anyways. I can just add those together and get a 0 first. So we're going to do that. Row, you can do them in any order. Just shear your sheep. Row 3 goes to row 3 plus row 2. And then I'm going to get 1, 2, negative 1, 0, 0, 0. And then 0, negative 5, 5. You can technically start being lazy and just get rid of that, but okay. This is going to go 5 plus negative 5 is 0. Negative 2 plus 5 is 3. And then what I'm going to do is row 2 is going to go to negative 1 over 5, row 2, and row 3 is going to go to 1/3 row 3. I am doing those two in the same one, and then we get a nice REF, which is 1, 2, negative 1, 0, 0, 0, never changed. 0, 1, negative 1, 0, 0, 1. If you want, I can go to RREF. This is REF. You practice doing this, but I would get this will be the RREF of this system. I have to kill this spot and this spot and this spot are the guys that we have to get rid of. Practice that. Try and see what you get. Long story short, what does this say? This says that we have the unique trivial solution only to this system. This says that x1 is 0, x2 is 0, and x3 is 0, and we call that the unique trivial solution. Those are actually what we are looking for when we do linear independence. We're looking for the unique trivial solution, then it's independent. You'll see when we get there. If we get not the unique trivial solutions, that means we found non-trivial solutions, there will be infinitely many, and that's bad, and that's not independent later. This system is relatively uninteresting. What that says is it only has a unique solution, and the only thing that solves it is 0. That's not good. So let's look at another one where we're going to have non-trivial solutions. Example 2, solve the linear homogeneous system below. We have another one. What's going to happen this time? I don't know. What do you do first? Augment the matrix. I'm already going to be lazy and put this one at the top because it's a 1, and I also want to multiply by -1. So I'm doing 2 moves before I start to make the system as fast as I want. I don't want to copy that out, and neither do you. Yes, you have to copy it out in every step. So I'm doing 2 and 1. I'm going to multiply this row by -1 to get a +1. Then I'm going to interchange these 2 rows, say. When I do that, I get 1, -3, 3 equals 0, 0, 0. That won't change anyways. And then what I've done is I put this row in the bottom, 2, 2, -1, and 3, -1, 2. There's a good starting point. So I want a leading 1 on the top left corner from the matrix. Nobody said you couldn't do it right from there. So as I formed the augmented matrix, I did a couple clever moves. Now I have a leading 1. I want to get rid of these. Therefore, row 2 goes to row 2 minus 3, row 1, and row 3 goes to row 3 minus 2, row 1. What is that going to give me? That gives me the top row won't change anymore. Once I have a leading 1, neither will that back column. I'm multiplying by -3 first. 3 minus 3 is 0. -1 plus 9 is 8. 2 minus 9 is -7. And 0 minus 0 is 0. Now what we're going to do here is multiply by -2. 2 minus 2 is 0. 2 plus 6 is 8. And 1 minus 6 is -7. Oh, I like this. Again, technically I'm supposed to get a 1 first, but you can see we can disappear a row. Row 3 is going to now disappear, and it was never there magically. Watch this. Row 3 minus row 2. What that gives me is 1 minus 3, 3, 0, 0, 0. 0, 8, -7, and 8 minus 8 is 0, and -7 minus -7 is 0. Therefore, I have, magically, it's gone. What does that tell me? I'm now in REF. You can go to reduced row echelon form if you want, but every time I can tell in the last row of REF whether I have infinitely many solutions, 1 solution or none. This time we have infinitely many. So now do you see, because I got the row of zeros, I don't just have the unique trivial solution. Before I start, I know it works. 0 plus 0 plus 0 is 0. 0 plus 0 plus 0 is 0. 0 plus 0 plus 0 is 0. It always works. Every time everyone forgets. 0 is always there. It's always a solution. I want non-trivial ones. If I don't get a row of zeros, this will never happen. I have infinitely many solutions. What does that tell me? Right here I have 8x2 minus 7x3 equals 0. What does that give me? That tells me immediately it's a line through the origin, which is the solutions. This tells me that x2 is 7 over 8x3, and x3 is free to be anything. Therefore, x1 minus 3x2 plus 3x3 equals 0, or x1 is equal to 3x2 minus 3x3, which is equal to 3 times 7 over 8t minus 3 times t, which gives me 21 over 8 minus 24 over 8t. That should be t as well, which gives me -3 over 8t. Therefore, putting that together, what am I going to get after I'd use the back substitution for this? This tells me that my infinitely many solutions to this homogeneous system is equal to x1, x2, x3 equals. x3 is t, x2 is 7 over 8t, and x1 is -3 over 8t. We have infinitely many. T is any real number. So this is the infinitely many non-trivial solutions. If you want the trivial solution, take t equals 0, and sure enough, it's still there. We want the non-trivial ones. Let's do another one. All right, example, I don't know where we are at, 3. Example 3. Now we're going to start doing, the first ones are just so you can get practice, but I really don't like just doing arbitrary numbers because you can't make any connection to this. Now let's go back and hopefully if you've already taken chemistry, I'm sorry, but if you're going to take chemistry, here's how you balance equations properly, infinitely many different ways. What they want is burning methane in excess molecular oxygen or atmosphere, which isn't the most prevalent gas. It's actually molecular nitrogen, which is the most prevalent. But either way, we have excess oxygen in our atmosphere. When you burn methane in excess oxygen, it produces CO2 and water, basically the smoke and the drippy drip out of your tailpipe, internal combustion. What we want to do is balance this equation, and then they get much more difficult equations, and they want you to balance these things, and then they show you some chemistry version of doing this. What it is it's linear algebra, and you're like, how am I going to take this scenario and create linear algebra? Well, linear algebra is everywhere because it's math, and math is everywhere. So if you're looking in chemistry or something, I guarantee I'm going to find it somewhere. What we want to do is balancing this equation. Here's the methane and the molecular oxygen and the carbon dioxide and the water. What we want to do is balance those. And what do we mean by balance that? So we want to have the same number of moles or amounts of each element on both sides of the equation. How are we going to do that? The way that we do it in mathematics is if we want to find x1, x2, x3, x4. It's like we need to find 4 unknowns somehow and set it up in some kind of linear system, and then hopefully we would have a method of systematically solving that linear system of 3 equations and 4 unknowns. How do we set this up? Here's how you steal the idea. What we're going to do with that essentially is, now what we have, because we have the power of algebra, and we've called it the unknowns here instead of just putting spaces like they do in the chemistry, and they're like, oh, let's ad hoc try and guess at what we could put in there and balance both questions. What we're now going to say is, I need x1 times this 1 carbon and 4 hydrogens to equal everything on the carbons and hydrogen on this side. So in the first one, first of all, in this one it's nice because I only have 3 elements, the number of protons inside. I have a carbon element, 6, I think. Hydrogen is 1, I know. Oxygen, 8. I don't know. Chemistry. They've got different amounts of protons inside. That gives them the elements. I only have 3 in this equation. What I want to do is balance the number of carbons on both sides, balance the number of hydrogen on both sides, balance the number of oxygen on both sides. For the first equation, for carbons, I have 1 carbon here, and it's multiplied by x1. So 1 times x1 has to balance on this side. What do I have? I have carbon here, and it's multiplied by x3. And there's where I get my first equation. I'm going to bring it all to the other side, and we're going to get a homogeneous. In the next one, hydrogens. I have 4 hydrogens multiplied by x1. And then on the other side, I have right here 2 hydrogens multiplied by x4, and I want to balance those. And I need to find x1 and x4 that will do this simultaneously. In the last one, hopefully you can see where I'm going with this. Oxygen has to have 2 oxygens here multiplied by x2, and then we have oxygen in both terms here, so we have 2 oxygens times x3. And 1 oxygen times x4. This is where I get these need to be the same. The x1, x2, and x3 and x4 are the amounts of methane, the amount of molecular oxygen, the amount of carbon dioxide, and the amount of water that we want on both sides. Once we get that, moving everything to one side and writing them equals 0, I get a linear 3x4 homogeneous system. And our theorem that we're going to state at the end of this to finish off this video is going to be, if you have less equations than you do unknowns, we have 4 unknowns, but we only have 3 equations. This has to have non-trivial solutions. I would hope so, because I would like there to be at least one, and in fact there's going to be infinitely many ways to balance this equation. Otherwise, internal combustion isn't a thing, and I'm pretty sure I usually say this, but I drove to the store today, so I'm pretty sure internal combustion is a thing, and so there must be at least one way to solve the system. It's consistent. If it's consistent and only has the trivial solution, that means you can only balance it with zeros. That doesn't seem right. It would seem like there is infinitely many solutions. How can I tell without even calculating? I have less equations than I do unknowns. So there has to be a free variable already. It's sitting there. Let's solve the system explicitly now that we know how to set it up. Moving that system up, we get, what are we supposed to do? I had a linear homogeneous system. We augment the matrix immediately. Now, this is the great part. I don't care where it came from in science. Now we're in math zone. I have an augmented matrix from a linear system. It doesn't matter where it came from when we're balancing equations. It doesn't matter. What do? You switch to the Pavlovian, augment the matrix, use Gaussian to REF, and decide whether we already know there will be infinitely many solutions. Let's do that. What am I going to do? Oh, I've got a leading 1, and it was the chemistry. I couldn't have even cooked this one up. The universe gave me a leading 1 in the top left corner. Starting with that, I have to eliminate this guy and get rid of it. What's that? You want to see? All right. Noodles wants to know how to internally combust things. Therefore, what are we going to do? Row 4, our row 2 is going to go to row 2 minus 4 row 1. What is that going to give me? 1, 0, minus 1, 0. 0, 0, 0 will never change. This row never changed either. And we're changing this one. 4 minus 4 is 0. 0 minus 0 is 0. 0 minus minus 4 is 4. And negative 2 minus 0 is negative 2. Now what we're going to do is get leading ones. Okay, you can go back. He's going to go catch some mice. I'm going to catch the solutions of this, infinitely many. Now what I do is row 2 is going to go to 1/4 row 2, and row 3 is going to go to 1/2 row 3, and we are going to get 1, 0, minus 1, 0, 0, 0, 0, 0, 0, 1, negative 1/2, 0, 0, oh, that should be a 1, 0, 1, negative 1, negative 1/2. Am I in REF? Not quite. These guys are in the wrong position, so interchange rows 2 and 3. And we're now going to get 1, 0, minus 1, 0, 0, 0, 0, 0, 0. Oh, I was interchanging the rows. Flip those. 1 minus 1 minus 1/2, 0, 0, 1 minus 1/2. Now I'm in REF. Once in REF, I can find the solution. What does that tell me? Here's a little tip also. This column has a leading entry. This column has a leading entry. This column has a leading entry. This one doesn't. X4 is going to be the free variable. The column that doesn't have the leading entry will be your free variable. Anyways, what that says is X4 is free to be anything. Then in this equation, this says X3 is equal to 1/2 t. Solving this equation, I move it over. In this equation, this says x2 minus x3 minus 1/2 x4 is equal to 0. This says that we get x2 is equal to x3 is 1/2 t plus 1/2 t, which is just a t. And x1 is going to equal what? X1, oh, we knew it from the beginning. The original equation told us. Forest for the trees, forest for the trees. Oh, he has to equal 1/2 t also because he's equal to x3. What does that give me? That gives me the general solution x1, x2, x3, x4, which is equal to, equal to, equal to, equal to, equal to. We're going to get to use the proton joke. We can't create half of a proton either, so we need integer solutions. So we're going to have to pick t as a multiple of 2. It has to be even. Therefore, what do we get? This was 1/2 t, t, 1/2 t, t. T is any integer. But really, to balance these equations, you have to pick t as a multiple of 2 or even. If you pick k equals 1, you get what chemists usually balances as, and you are going to get the solution x1 equals 1, x2 equals 2, x3 equals 1, and x4 equals 2. What does that mean? To balance the original equation, if we pick specifically and we want to balance this, we know that our parameter has to be a multiple of 2, so we get whole. We can't have half of a hydrogen atom or half of a hydrogen molecule, because hydrogen only has 1 proton. You can't split this in half. It has 2 up quark and a down quark, or some combination of this. I can't remember. Physicists will know. But when we do this and balance it, tie it back to the original equation, what that says is we needed 1, 2, 1, 2. This is how we balance. Example 4, we're just going to ask a question. And this is the power of using our intellect and strategy and theorems and results instead of having to brute force calculate. Yes, at first you just want to brute force calculate, but I'm going to not row reduce or even augment this matrix, and I can answer this just by looking. This is the point of the theorem that we're about to do. Does this system have non-trivial solutions? Remember, 0 always works. 0 minus 0 plus 0 is 0. 2 times 0 minus 3 times 0 plus 5 times 0 is also 0. So that already works. We know this is consistent. Do we have non-trivial solutions? And I can immediately say yes, because I only have 2 equations, but I have 3 unknowns. So that means that there's already secretly sitting a third equation if I'm going to look at a 3x3 system. So there has to be solutions which are non-trivial to this system. How do I know that, or how do we say that? Yes, this has non-trivial solutions. Why? We have 2 equations and 3 unknowns, and that says at least 1 variable is free to be any number. We don't have enough information in the system to lock down everybody uniquely, So there can't, and we know that there's the trivial solution, so there can't be the unique trivial solution. So there has to be non-trivial solutions every time this happens. It's not just this system. What is it about this system? And can you see what we're saying here with the theorem? Why does this scenario guarantee that we have a unique solution, but if I add another non-zero row, I'd actually have the row reduce and check? The theorem is going to say anytime you have that m equations is less than n unknowns, you always have non-trivial solutions to a homogeneous linear system. That's what they're getting at. Let's state that explicitly and be done with this chapter. Okay, explicitly to end the chapter, what we're saying is if you have a homogeneous system where the right-hand side is all zeros, if the number of equations I have is less than the number of unknown variables, and then algebraically we say if m is less than n, and you forget what those pieces mean. But if the number of equations that I'm given in the system is less than the unknown variables that I have, the system always has non-trivial solutions, and that's what we're looking for. Non-trivial solutions to homogeneous equations. Please subscribe right here, hit the notification bell. I'll see you in the next chapter.